Okay, welcome to this seventh video in the series of videos on factoring. If you're here, you should have already seen the overview of factoring video, and you should have watched videos on factoring expressions using greatest common factor, difference of two squares, perfect square trinomials, and both quadratic trinomials of easy and hard form. This video I'm going to split into two pieces to give some focus to the prerequisites when we work with sum and differences of two cubes, because they're a little less familiar than squares. Okay, so let's drill down into the concept map and let's take a look here to develop some ideas. One thing we want to see is that sum and difference of two cubes, when we are asked to factor them, they are done by a special pattern, and I will demonstrate that pattern as the video progresses. Then we're going to take a look at some of the prerequisite skills for sum and difference of two cubes factoring. They are identifying a perfect cube, cube rooting perfect cubes. I'm going to spend some extensive time on that. That'll be the predominant part of this video. Then also squaring a given term, you'll need that skill. You should have it if you're already here. And most times when we've talked about checking our factoring work, we've talked about FOIL. The pattern involved in sum and difference of cubes is not a FOIL problem. It's actually going to be a binomial times a trinomial, so you'll need that skill to check your work. So this video will talk mostly about the prerequisite skills. The next video, I will try to develop the steps for factoring a sum and difference of cubes, and we'll try and end the video putting that here. So let's take a visit over to some other materials I've made here, and we'll talk about identifying a perfect cube and cube rooting perfect cubes. In terms of identifying a perfect cube that is a constant, or the coefficient of a term, we need to realize that the perfect cubes are generated somewhat like the perfect squares, which were 1 squared, 2 squared, 3 squared, except they're going to be 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, 6 cubed, etc., etc., etc. More importantly, these numbers become 1, 8, 27, 64, 125, and 216. Again, note that this pattern does go forever. It's a little hard to know our perfect cubes because the exponent is larger than the perfect squares, making the pattern grow more quickly. You should know the first 5 or 6, and you could always go to your calculator. If you suspect something is a perfect cube, just cube root it and see if you get an integer. Now, the variable rule that we want to be able to commit to memory and be able to apply with regard to identifying a perfect cube is a little different. It's going to strictly look at the exponent, and I'll just tell you what it is. The exponent has to be a multiple of 3. Okay? This is important. We saw with squares they had to be a multiple of 2 with regard to the exponent, and you would probably guess if something were a perfect quartic, which is a 4th power, it would have to be a multiple of 4. So I'll just give you some examples here, and then we'll look at some combined examples that have coefficients and variables. But for instance, we see that the most basic cube we can talk about is x cubed. And that should be pretty obvious because obviously 3 is a multiple of 3. Then something potentially like b to the 9th would be a cube because 9 is a multiple of 3. And then something maybe that had 2 variables, something like m cubed b to the 12th. This would be something that is a perfect cube. So if I just combine these two ideas here of coefficient and variable, it would have to be, the coefficient would have to be something from this list, and all the exponents that appear for the variable parts would have to be multiples of 3. So something just like, oh, I don't know, let's say 64x to the 15th would be a perfect cube. Okay? Um, this is important to be able to recognize these things because you're going to have to then, as part of the factoring process, cube root these perfect cubes. So let's talk about that now. Okay, in terms of a coefficient, if we look over here at our coefficient list, where we have 1, 8, 27, etc., just cube rooting it means you're going to work back to the base in the previous line. Excuse me. So the cube root of 27 is just 3. Similarly, the cube root of 125 is just 5. Because don't forget, these are a reversible process, the process of cubing and cube rooting. Okay, so just to give you an example here, we say that the cube root of 2 cubed is equal to 2, which is a property you should know. Similarly, if it weren't written as 2 cubed, the cube root of something like 125 would just be 5. So in variable expressions, it's just a little bit different. Okay, for variable expressions, you might be able to guess what it is already. We wanted the exponent to be a multiple of 3 because to cube root it, you will just divide the exponent by 3. Okay, so if you were to have something of the nature of x cubed and we decided to cube root it, you would in fact get x to the first and not need to write the first power. Okay, similarly, if you had something more complex, such as something like 216 x to the 9th, b to the 6th, we would be able to notice that that is a perfect cube very quickly, because 216 is in the magic list, and 9 and 6 are multiples of 3. So just creating its cube root would be the cube root of 216. Let me just write my little cube root process here, and that's going to be able to give us the cube root of 216 is 6, the cube root of x to the 9th is x to the 3rd, and the cube root of b to the 6th is b squared. So I hope this has been a good explanation and review of, or insight, maybe it's not a review, as to how to identify perfect cubes as well as take cube roots of perfect cubes. Okay, let's take a look at what we meant a little bit by this special pattern. Okay, the special pattern for sum and differences of cubes is what allows us to write the factored form. Right here we see that we've got the sum of cubes factors into this special pattern, and if you notice here, the difference of cubes factors into this special pattern. Okay? I'm just going to, for a moment, just examine the sum, and then I'll look at both of them together in just a second. So, if we notice, a sum of cubes is just that. It's an addition of 2 cubes. We know that these 2 terms are cubes, obviously, because the exponent is 3. So if we now start to look at some of the components in what will be our factored form, or our answer, for lack of a better word, we see that we're going to need to be able to see a relationship between L cubed and L. Well, I hope you guys see that that relationship is that you'll cube root the L cubed. That's why we just reviewed about how to take the cube root of a perfect cube. It's the exact same story for turning R cubed into R. You will take the cube root of R cubed to do that. Well, once you have L and R, it's pretty easy to go from L to L squared and R to R squared. You just take those individual factors and square them. Okay, so you should totally have that skill when you come here. Just be able to square something means to raise it to the second power. Now, the only thing left, if you notice, we've sort of like take a little checklist here. We just talked about how to create L and R, creating L squared and R squared, and then the last piece is just doing L times R. Well, that's as simple as taking these two pieces and multiplying them together. So if we notice, the difference of cubes has absolutely all of the same components. From L cubed we go to L, and from L we can go to L squared. From R cubed you can go to R, again by taking the cube root, and then from there you can go to R squared by squaring it. Obviously, once you know L and R, you can figure out what LR is by multiplying them together. So if we look at these together, you notice that they're almost identical. The only thing that is different from one to the next is the sign pattern. So I'm going to try and give you something that's going to help you memorize that sign pattern. Okay? So let's toy around with it and see if you can build this model in your head. Well, for the sum of cubes, when I write the answer, the sign in the binomial is also a sum. And for the difference of cubes, the sign in the binomial is also a difference. It's minus. Okay? So the one thing that I tend to say about the sign in my first part of the answer, I say it's that the same as the given sign. So if you notice here, I'm going to put a little s with it for same. Now, if you noticed the next sign, well, which is here and here, you'll notice, well, in the one that is the sum, it becomes different and becomes a difference. And the one that starts as a difference becomes different and becomes a sum. So I'm actually just going to put the letter D here for different. Okay? So what does that mean when we come to the third sign? Well, let's see. Well, in both of them, it's just positive. Well, then I'm just going to label that with a P for positive. So if you notice here now, if I took out the signs, this would be completely a way modeling how to practice regenerating the signs, and it's pretty simple. It's using the SDP method. That's how I get kids to memorize it. So what do we do with that? Well, if you're given a sum, okay, I'm going to do the same as the given. In this case, it was plus. And different from the given, which that would be minus, and then the positive is just positive. Well, if you notice, if you compare that to the top line, that works because they're identical. So if I take those out and see if I can apply the same thing for the difference of cubes, let's see if we generate a correct answer. Well, the same as the difference is a difference. And then different from that would be a plus sign, and then finish with positive, because they both do. So if you notice, that would help me generate that special pattern. So in the end, the only thing that you really have to memorize in the pattern is two things. You have to remember that L cubed, R cubed, obviously with this little space in here for a sign, but when you have L cubed, R cubed, it will be the product of LR, then L squared, LR, R squared, and then SDP for the sign rule. Okay? With a little practice, you can master that. The purpose of me trying to show you this way is so you don't have to memorize two rules. Here I'm just memorizing the sort of skeleton of the letters, and then I do the signs using this SDP phenomenon. So take a little practice with that, and again, you have to memorize this. There's not a way around that. You can't apply a pattern that you don't have committed to memory in these problems. So let's go back a little bit to the skill of identifying perfect cubes and cube rooting them, and take a look at how we're going to combine that with a special pattern here and generate an organizer that will help you actually factor these problems when I give them to you. Okay, so if we look at this chart, in the top row, I have a bunch of perfect cubes. Okay, so if you notice here, the top row is all things of the form a cubed because they're all, in fact, cubes. The coefficients are from the magic list, and all the exponents are divisible by 3. Oops, except that 8 that I just turned into a 9. The power of editing. Okay, so then this middle row will contain all squares, and the bottom row will contain all the roots. Okay, so to fill this organizer out, you have to be able to do it in this order. When given the cube, you have to go to the cube root and then come back up to the square. Okay, it's not possible with any ease to come from this row of cube to square. Okay, mentally it's not easily, at least. So we're going to take a look at filling out this chart now. Okay, and if I try and take the cube root of m to the 6, it will be m squared because I will divide the exponent by 3. Now, if I were, in fact, going to square that to come up to this row, it's as simple as multiplying the exponent by 2, giving me m to the 4th. Similarly, to be able to take 27x to the 9th, that is a cube, and come down to its root, it means I have to be able to cube root the 27 and cube root the 9. Well, the cube root of 27 is 3, and the cube root of x to the 9th is x to the 3rd, because I will divide the exponent by 3. Now, to take the root and create a square, I will square the 3 and square the x cubed, which is going to be able to give me 9x to the 6, because you will multiply the exponent by 2. I hope you start to notice in this pattern that the bottom two exponents, the bottom and the middle row exponent add up to the top row exponent. 3 and 6 is 9, and again, like I just showed, 2 and 4 is 6. Okay. Also, if you notice, the coefficients of the bottom and middle row multiply to the top row. So 3 times 9 is 27, and 1 times 1 is 1. Okay. Continuing on, or better yet, why don't you hit the pause button and try to finish this chart, okay? And I'll have the answers here just when you come back. But take a second and do that. Remember, to go to the bottom row, you got to cube root the coefficient, and then divide the exponent by 3 to cube root the exponent. Then to go from the bottom row to this row, you'll have to square that answer, which means to square the coefficient and multiply the exponent by 2. Okay, I hope you have a chance to compare your answers now and have practiced this skill some, because you're going to need to replicate a chart like this to actually do the factoring. Okay, so this seems like it checks out, right? 3 and 6 is 9, 4 times 16 is 64. Again, for this row here, I cube rooted the 125 to get the 5, and I divided the 27 by 3 to get 9. You have to be careful there. Some people think, oh, I'm cube rooting 27, so I should get 3. But again, to cube root an exponent, you divide it by 3, not actually cube root it. This one on the end here, well, the cube root of 1 is 1, and 1 squared is 1. Don't forget that 1 is a perfect square, a perfect cube, a perfect fourth, a perfect fifth, because it's the first number in all of those magic lists. Okay, so I'm going to end this video here. I'm going to pick it up with the next video, which will get right into some factoring models. So feel free to go to that if you have this one secured. If you don't have this one secured, go back and look at some pieces